Okay, so hi everyone. My name is Maxime Mouchet. For those who don't know me, I'm a postdoctoral researcher at the Lipsis laboratory at Sorbonne University. And I'm part of a team where we build tools and systems to capture the topology of the internet. That is the set of routers and all the interconnection between them that makes the internet as completely as possible and as fast as possible. So people have been working on this for a long time, especially at the Lipsis. But you try to scale this to the whole internet. And so far, we've been focused on providing data to the community, but we didn't play much with the data. We didn't analyze the data or try to visualize the data. So today, I'd like to present you a kind of side research project that is important to me, which is trying to visualize our data. Basically, visualize very large graph of the internet with millions of nodes and edges, and see what we can do with this. So it's going to be a very visual presentation, and I hope you will like it. Don't hesitate to stop me, ask questions. I will try to make things as easy as possible, even for people who don't know at all how the internet works. So let me know if you have any question at any time. So a question I had for a very long time, and even during my studies, what is the internet, right? Some people, my professor were telling me it's an interconnection of network, but what's a network? Where do they interconnect, and so on? And in fact, it's internet is ubiquitous, right? Like electricity and water and so on. But few people really know what is the nature of the internet, right? And Kevin Kelly, which for the anecdote is the founding executive director of the Wired magazine, if you know Wired.com, in 2009, he asked people to draw the internet. So he said, please draw a map of the internet, say where is your home and what you do in life and so on. And it's very, very interesting, I think, to see what people think of the internet. So some people, they do some complex drawings with with some technical stuff like some satellite antenna. A lot of people think that the internet goes through satellite when in fact it does not, but it's kind of drawings. More abstract drawings where like, everything seems to be connected together. Well, people lost in the internet. Some more realistic maps. So this is like the hand-drawn map, but of the ARPANET, right? The original version of the internet, the ancestor of the internet, and a mix of things like some routers and also some websites. For most people, I think the internet is the web, right? When in fact the internet is much older than the web. But for most people, internet is website. There's a lot of hundreds of pictures on his website about this. And something interesting is that psychology professor at the University of Buenos Aires, she studied the drawing, and she made some statistics, and one on the topology of the network, like how do people represent the network. And it's interesting that more than half of the people, they represent it as either fully connected or a star, when in fact internet is more like a mesh, but it's neither one of those. And so the question is, what is internet? How can we visualize internet in a more, not scientific manner, but with data and so on? One way of doing this is by visualizing the allocation of IP addresses. So you probably know that there are around 4 billion IPv4 addresses on the internet, and these IP addresses are assigned by block to Regional Internet Registry, RIR. There are 5 in the world, one for North America, one for South America, one for Europe and Middle East, one for Asia Pacific, and one for Africa. And this registry, they then assign IP addresses to operators, companies, and so on. And originally, these blocks of IP addresses were given to companies. So you have these blocks. Here we will represent blocks of 16 million IP addresses. So there are 256 blocks of 16 million IP addresses. And one way to represent this block in space is by using what's called Hilbert curve. And an Hilbert curve is a way of filling the plane in such a way that, in this case, for IP addresses that are closed, for example, all the IP addresses starting with 0, all the ones starting with 1, 2, and so on, up to 256 here, they are closed in space. And so you can do this kind of map. Originally, this was suggested in 2006 by Brendan Munro of the XKCD comics, where he made this map showing which registry, so all these IP addresses, for example, belong to Europe, those to America, and here you can see the first IP addresses that were given to the first companies, part of the internet, right? Like Bell Labs, Apple, the MIT, and so on. And also you can see a lot of free space because it was 15 years ago. Now, of course, it's full. As you may know, there are no more free IPv4 addresses. So this is one way, right? This is kind of the internet, the way IP addresses are allocated. You can push this concept a bit further by actually measuring what this is only the allocation, right? But you can, for each, so here the resolution is higher. It's not blocks of 16 million IP addresses as before, but blocks of 256 blocks. So here we have 16 million pixels, each representing 256 blocks. And for each of these blocks, first you look if it has been assigned to someone. If it's assigned and also routed on the internet, that is, you can join it on the internet. And if there are computers behind, if you can ping some addresses inside, send a message, and you get a reply. This one is from 2013. It's made by CAIDA, the University of California, San Diego. And you can see where there are devices on the internet and where there are not. And for example, you can see that a lot of the blocks that were assigned to companies in the past, they are not routed on the internet anymore. They are assigned to the company, but they don't use it. Probably that since then they maybe have sold them because you can sell IP addresses for a very high price. Now you can push this concept a bit further by doing measurements like every hours, for example, and on each blocks of 256 address, and see kind of the heartbeat of the internet, right? See a device coming on and off. So here, I think the more blue it is, the less device, and the more to the right we go, the more device in this. So here is just a small block of 16 million addresses. And you can even, so here the layout was based on the, but you can geolocate the devices, and you can make this kind of map where, well, it's the same as before, but geolocated. So something very interesting and that I learned in making this presentation about this visualization, actually it was made by an anonymous researcher / hacker, because to make this map, basically they scanned the internet to find boxes, ISP boxes like routers with the default password, which was not changed. They logged onto the routers and they performed measurement of the internal network, of the home network from the router, right? So they were able to see much more device than what researchers usually see, right? Because usually if you target an IP address, you will see the router, but you don't see, I mean the home router, but you don't see what's behind. This has been debated in the community whether it's a good idea or not to do this, and even as a researcher, if it's difficult to use this data or not. I never did because I was not aware of this data set, but this exists. And anyway, it makes for a nice presentation. Here, the data is geolocated, but as we will see later, and as you may have, you may know if you follow Kevin's talk from a few weeks ago, it's not very easy to geolocate. And in fact, this geolocation may be inaccurate. And then we have more like infrastructure maps, right? So this is a map which I really like, and since I've discovered it years ago, of the submarine cables, which, you know, when you discover that the internet is made of submarine cable, it's, I think, very impressive, and the scale and the number of cables all over the world. And well, this is a very detailed map. And at the difference of the previous visualization, it's an infrastructure map. Right? It shows what the internet is made of. It's very precise, and you don't need measurements to make this map. It's only administrative information. Probably that most of this information is also publicly available, which will contrast with what we will see after, but it's operators network. Usually operators, they don't communicate what their network is made of, with which other network they peer, and so on. So so we'll have to perform measurements. Yes. So how do we get more detailed infrastructure map, right? Because here we have the submarine cables, but we want to know what's inside France, what's inside the networks of operators in France, and so on. The first way to do this is to exploit the routing protocol of the internet, which is called BGP. For people who know how this works, I'm sorry, it's going to be really simple, but it's for everyone to get it. Basically, the internet is an interconnection of network, right? An autonomous system, an AS, can be an operator like Free, Orange, or whatever, a company like Google or Netflix, a big company, or an academic operator like Renater, and so on. And they are interconnected. And each of these autonomous systems, they are made of routers, right, which forward the traffic. Let's say that some autonomous system, they have a network 1 here. And how do other autonomous system knows that this network exists, right? The way it works is that BGP protocol, with the BGP protocol that is used on the internet, is that this AS, which we say peer with this AS, will send a message saying, I can reach network 1, okay, and with his name. And then AS2 will communicate to its peers, saying, I can reach N1 through me, and then through AS1, right? And this way, AS3 knows that to reach N1, it needs to send packets to AS2 and AS2 to AS1. Now you can make use of this fact that this, called the AS path of AS, that from the origin AS towards where you listen. If you have access to this router, you can look at the routing table and look at least the BGP messages, and look at all the messages like this, and you can infer from your point of view the interconnections between the autonomous systems. So you can know, for example, just by looking here, that 2 and 1 they are connected. This is a very popular way of doing things because you just exploit the way the internet works. You don't need to make any particular measurements. It's what's called passive measurement, right? You just listen to things. So now, if you do this, you will have a graph basically saying AS1 is connected to AS2, AS blah 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 to AS blah blah blah, and so on. But how do you visualize this, right? There's approximately, I think, 100,000 autonomous systems on the internet, something like this, maybe more. I don't know. One way, it's what's called AS core visualization, where the longitude, I mean the angle on the circle, it's the longitude on Earth, right? So, well, depending on where something is in Europe, it's going to be more here, Africa also, because it's longitude overlap with Europe and so on. And the distance to the center is inversely proportional to the number of customers of the size of the customer cone of an autonomous system. So the customer cone is the number of clients of an autonomous system, but also the number of clients of the clients and the clients of the clients of the client, and so on. So in the center, we have autonomous systems which have a lot of clients. They have a lot of clients which themselves have a lot of clients, and so on. And at the edge, we have autonomous systems which have no clients. When I say clients, it's not you and me, it's another autonomous system, right? So this has basically what we sometimes call eyeball networks, which is basically just people, you know. It's not always eyeball, but at least service providers, and with just people, the traffic ends here to people, but it never goes to another IS. And so with this kind of visualization, you can kind of see which are the ASs which makes the core of the internet. So it's a nice visualization, but well, you can't really see what's happening everywhere else, right? But at least, and this will be your problem afterwards, here you have an easy way of computing the layout. Right? The layout is longitude and size of the customer.
Maxime,
yes.
So the thing is the mouse, because you're not film.
Ah, yeah, right. Okay, so I was, yeah, sorry, I was showing with the end, but I think you understood for people online that.
For the next.
For the next, I will explain. Okay, sorry. If you have any question for the people online. So the issue basically now it's of if we want to find another visualization, it's to how do we lay out a large graph, right? And there are many, I think you probably know better than me, graph visualization algorithm. If you are naive as me, you try to load a million edges, million nodes graph into a tool like Gephi, and then it crashes your computer. But one algorithm that has been particularly successful, it's what's called the large graph layout algorithm. So it's an old paper from 2004, which was originally made to visualize biological data like relation between proteins and so on. I can't tell you more about this, but basically it's a very simple algorithm. From the graph, you take the minimum spanning tree of the graph. From this minimum spanning tree, you choose a root node, however you want, the node which minimizes the distance to the other node, so whatever you prefer. And then from this root node, you take all the nodes which are at distance 1. So you take all the nodes which are at distance 1 in the minimum spanning tree. You lay out this node using some attraction repulsion mechanism. Then for each of those nodes, you take the nodes which are at distance 1 of these nodes, and then you lay out them and you repeat the process and so on. This has been used for the this has been used for the first time to visualize AES, autonomous system relationships data, by Barrett Lyon, which created the Opte project. So it's an image from 2010. And here, each edge is an interconnection between two autonomous systems. And also at the end, the leaves, they are the prefixes, networks, which belong to this AES. And so, so this one is kind of dense, but still, I like it. And so it's one output of this algorithm with a very large graph of the internet. Now you can also animate this, right? Because this is based on BGP messages. You can listen to BGP messages over time, which they are thousands per second, and animate how the internet is evolving. This video shows the internet blackout in Iran in 2019, where the government cut the internet to try to suppress some protests. And you can see it at here on the upper left of the layout. And here in real time, you can see parts of the network disappear and appear, right? So I think it's a pretty interesting thing to see. Now, this is at the autonomous system level, right? But as I've said before, with BGP, you don't see all the routers. And I'm sorry for the people online because I can't show the mouse, but you can't see with BGP, you don't see the routers in the networks, right? You will see that AS3 is connected with AS2 and AS2 with AS1, but you don't know that there are 4 routers in AS2 and so on. So one way to make these measurements is to use a traceroute measurement. So I'm sorry for people online, my mouse doesn't show on the screen, but I will show on the screen here. The way we detect routers on the internet is by performing an active measurement this time, which is called traceroute. And the way it works, so suppose we have the same networks as before with routers. The routers, they have interfaces, right? So an interfaces is just a port, right? Like an Ethernet port or optical fiber port. and you have host computers, right? Here I have my computer, for example, host1, and I will send a message to a computer somewhere else, like host2. But I will say that, and this is a feature of the internet protocol, of the IP protocol, that I want my message to have a time to live of 2, which means that after my message has crossed 2 routers, I want the message to expire. This is a mechanism that is in place to avoid routing loops in the network. And so if I send a message to H2, but I say I have a time to live of 2, then when I cross the first router, time to live goes to 1. And when I reach the second router, time to live goes to 0. And this router sends me usually a message saying time to live exceeded, to inform me that my message was lost. But what's really interesting is that because you receive a message from the router, you know that there's a router, and you know the IP address of the interface close to you of this router. So now I know that on the path to H2, I have alpha 2. You do this on and on. So then you go to send a message with a time to live of 3, 4, and etc. until you reach the destination. And if you do this for the whole path here, you will get something like alpha 2, beta 2, gamma 2, epsilon 2, eta 2, and so on up until the end. So that's the way it works. So first, it's much more, you need to actually send packets on the network, right? And in the scans we do of the internet, we send billions of packets over a few hours to do this measurement. So it's very costly in terms of bandwidth and of network measurement. But also there's many issues which I won't go into details here. But for example, there's techniques to detect that here you have multiple paths and so on. So we perform, and I will come back to this, but we perform multipath measurements.
Maxime,
yes.
Est-ce que tu peux aller voir dans les icônes de zoom là tout en haut?
Ouais.
Je vais peut-être te trouver un pointeur.
Alors.
Est-ce que tu as un truc qui s'appelle annotation
oui.
annotate, et dedans tu dois avoir spotlight. Voilà. Et là normalement avec un peu de chance.
Ouais, mais il va me falloir que je redémarre la zoom.
Ah oui d'accord.
Parce que je l'ai pas autorisé encore. Je sais pas pourquoi la souris apparaît pas, mais.
Au cas où.
So that's the way we infer the path. But most importantly, Traceroute does, while BGP updates, you can infer a succession of AS. With Traceroute, you don't infer a succession of routers, right? You will not know that there is R1, R2, R3, R4. You will know that there's this interface, alpha 2, beta 2, and so on. So this is important because, for example, if I were to do the same measurement, but from H2, I will see the interface beta 1 of R2 because the message will come like this. But from H1, I see alpha 2. And the process of knowing it alpha 2 and beta 1 is the same IP. It's called alias resolution. It's a whole other problem in the field. So in the maps made with Traceroute, I will show after, the graph is made of interconnection between interfaces. So an edge will be alpha 2, beta 2, and not R2, R3, right? Or not beta 1, beta 2, but it's going to be edges between interfaces. So keep this in mind because it's not really maps of routers. It's a map of links between interfaces of routers. The first map made with Traceroute I could find, it's from a paper called Mapping and Visualizing the Internet from '98 from researchers at Bell Lab in the US, where they made this map with, I think, 10, no, more than this. They made the measurements toward 100,000 networks, academic networks. I mean, the internet was small at the time, right? So, and they made this graph, but I think the layout algorithm was not so nice, and maybe also because of limitation of compute resources and so on at the time. Well, they made this map, but I think it's not very usable in itself. A work which is more recent from 2005 from Mathieu Latapi at Sorbonne University. So they perform trace routes towards a lot of destinations on the internet. Here it's only 2,000 IP addresses which were destination IP addresses which were targeted. This is a smaller map, but I think because of the small number of links and edges, here the layout is better, right? It's easier to read, and then maybe you can zoom and see what's everything. And as we will see after, it's an issue when you want to try to visualize a very large graph, is to be so is to have something that is readable, right? You can see what are the individual edges and so on. So again, Barrett Lyon from the Opte Project, which made the yellow map from before with BGP updates. He also made one before in 2003, the first map he made with Traceroute. And actually, this map was very successful. It has been exhibited at the Museum of Modern Art in New York and also other museum. And I think it's something important in the sense that, you know, research paper, they don't end up in Museum of Modern Art. And I think while I agree, and we can agree that this kind of maps, even though I will try to show you, maybe we can do better, but they are not very useful for research, right? But at least in communicating to the general public, what is the internet? Here in a single picture, you can see what's the scale, where internet is dense, where it's not dense, depending on the coloring, and I will show you that after. You can see different features of the internet. So, so I think it's important to, at least for me, to spend time on visualizing the data, even though from a research point of view, the interest may be lower, because it helps communicating with people what's the internet and so on. So in this map, there is 100,000 nodes. And in the map, I will show you right after, so that we do, with the measurements we do, and which I think are the most complete publicly available measurements of the internet right now. So here there's 100,000 nodes. In the map we make, there's 1.5 million nodes and 3 million edges. So this is a map that I've made from measurements we have in July 2021 of last year. So here it's full multipath measurements with 3 million edges. Here the coloring is the same coloring as in this map, not the same color, but the same way of coloring, which is by regional internet registry. So in blue, it's North America. In yellow, it's Asia Pacific. Maybe green is Europe, and the other colors, I'm not sure. I should have put the legend, but it's colored by internet registry. And well, first I like it. I think it's quite nice. But well, we want to know more, right? Like, what are these two big networks here? So it's China, but we will see after. This is Google network and so on. And but we would like, you know, to zoom and to see what's inside, what this map is made of, and so on. And until now, there was no way to. So before seeing this, we can also. So this is the layout for the full map, but we can also lay out individual networks, right? So this, I just take here the subgraph, which is made of the node in the Google autonomous system, and I lay out. And what's interesting is to compare different networks and the way they look. So Google, we seem to have this core network with kind of edge sites. But here it's a very, very dense network, and we will also see it on the map from a Chinese internet service provider. Well, like everything seems to be densely interconnected. And at the opposite, we have here Deutsche Telekom, which is an internet service provider, and the big stars, or Kiwi, as Fabien calls them. This is kind of not a measurement artifact, but when we perform the measurements, we want to identify only the routers on the internet. So we always exclude the last IP, which is a computer, right? We perform measurements towards computer, but we keep only routers IP address. So basically, here it's kind of all the links here, they are the last hop before someone else, router or something like this, box or whatever. So here we have a lot of customers and some kind of backbone networks. So this is nice, but not very useful. So now what we want to do is to take this map, right? And
I think I disagree with you. I think it is useful because you you have a way to visually show that networks may be very different from
very different structure. And then we can discuss this afterwards, because the way they look may also be biased or an artifact of the layout algorithm and so on. But at least it's interesting that with a very simple layout algorithm, which doesn't take into account anything from the network and so on, we have this kind of layout image, right? Now we will want to take this map and making more interactive, right? And at first I tried many things and I was like, so yeah, making this image is very fast. But if we want to zoom, we need to make a very high resolution image, right? I made images up to 16,000 by 16,000, so 256 million pixel images. But even with such a large image, which is already, you know, slow to navigate with your computer, the resolution is not enough to see all individual edges, and if you want to add information, you need to somehow handle the zoom levels and so on. And I was like, how am I going to do this? But then I realized that this is what probably other people have realized this, right? But this is what is already done for Google Maps and all these kind of maps on the internet, right? Finally, you have roads, which are very large graph, and depending on how you zoom, everything is handled automatically, right? You show less feature when you unzoom, more feature when you zoom, and you can do everything you want on the map, right? You can draw path, you can add point of interest, and so on. And so then there's also like Google Maps, you have to pay to use it, and also you can't really display this kind of data, but there are map tools which are free and open source, and I will discuss how to use them right after. So I reuse this tool, and yes, the most important part, it's what's called tiling when making a map, whether it's a map of the internet or converting your data to a map. So basically, it's just that you cut the data into tiles, which are indexed, you know, by the latitude and the longitude. And depending on the zoom level, you aggregate the features on all zoom level. So that when the zoom level is low, very high level view, you have a single tile, but with few features, only the most important features. And as you zoom, you add tiles. Very simple process, but there are already thousands of tools, I mean, hundreds of tools on the internet that does. So how do we do this? So first we need to make a measurement, right? And compute the links. Here it's more technical things, but just to say that right now I exclude a lot of bad data from the measurement, maybe that I can include later, but all the nodes, when we do Traceroute, sometimes we have what we call stars, which is mean a router, but we don't know the IP address of the router. So I exclude all of this node, all the prefixes which sends us more replies than we have sent probes, the one routing loops, and also unlikely links, because sometimes we have weird data like some Korean ISP, then Google, then another Korean ISP, but there's no reason for this. So I have some heuristics to clean up the data. And here we lose a lot of data because in the original measurements, we have 5 million edges, and here we keep only 3.5 million. Then out of this node, I take the largest connected component of the graph. I compute the large graph layout, but it could be another layout. I add, and I will show this right after, but data about the autonomous system, the allocation of the IP address, the facility, whether it's an internet exchange point, and so on. And then we generate the tile set by dropping, but this is done by the tool, but basically in zone where it's too dense to drop some small features at the lower zoom level. So I will show you quickly the tool, which is a work in progress, but to see what we can do with it, and then future works. And we can conclude. Oops. So basically, this is what you have if you take the graph I've shown you before and you put it in a web map to the right. So it looks like a map, and so you can do cool things like show titles of the countries, but here it's the biggest ASCs in the graph, and also you can zoom on parts of the network, and it will automatically load. You can see things appearing and disappearing as you zoom information. So what is very cool, I think, myself, is that here we have a very, very large graph, like with millions of edges, and it's it's like very, very fast, right? At navigating this graph. And so if you want to know what is something, so I told you that these large orange blobs, they are China, but Chinese network. But if you want, you can zoom and you can see like, okay, what are these individual IP addresses and to who they belong. Obviously, it's messy because there are millions of links, and maybe there are ways of, maybe we can reduce useless links, we can aggregate links according to some rules, we can use a better layout algorithm. But this kind of, the idea of reusing map tools to visualize graph which the layout have already been computed, you can use the layout you want, right? If one day I find a better layout algorithm, it doesn't change the fact that you can do this. But you can also filter things, right? If you want to see only things in Europe, you can choose the European Internet Registry, the RIPE NCC, and then you see only, so I should remove the titles, but forget about the titles, but now you see only the networks which are registered in Europe. You can also filter by autonomous system. So for example, you want to see, so maybe there should be a search feature, but let's say you want to see where Google is, right? You can show only Google, and then you can see that Google is here, and you can check Google network, and you can also see like interconnection between Google and other networks. But you can also have other colorings, like for example, you can show only you can not color by internet registry, but by classification, whether it's a service provider, which kind of company it is. So this classification is not very good because the main classification, almost all of the edges, they belong to the computer and technology class. But we can probably use other classification to visualize the edge. Maybe you also, maybe you also want to know like where to network. So before this, so if we look at networks like Google, they are quite dense, right? Because they are not a service provider for other networks. They are not a transit provider. They are a destination autonomous system. So they are in one part of the map. But you can, if you look at transit providers like level 3, then you can see that they are all over the map, right? The same for Cogent, which is one of the largest transit providers. They are also all over the map, right? And you can see that they pair with a lot of different networks.
Just have a question. Apparently, it looks like a sphere, but there is no relation with the geographical.
No. So I will. Yeah. So as I said, we can use whatever layout we want. Why do I use this large graph layout algorithm? So first, because it's the only layout algorithm that I found that is, that you can compute in a few hours for such large graphs without any additional information. And it's visually, it's reasonably, it's nice enough, and it tends to cluster networks. The clustering kind of makes sense, right? If that transit provider, they are all over the place, but that Google and dense network, they are in one place, that makes sense. And also, obviously, what would be nice is to have this, to have the map background and the real geographical position, right? But geolocation is very hard. Even works like the one of Kevin is 10% of the. Okay, Kevin, 30% of the routers which are correctly geolocated. So for the 70 other person, we don't know where to place them on the map. So it's because it's hard to have geographical information, and also because
and maybe it's not also the right.
Yeah, maybe it's also. So, but for sure, for instance, one issue with this kind of algorithm, so if we look around Google, is that it has trouble with troubles to lay out what we call a diamond. So you see this kind of weird stars here. In fact, they are diamonds, so they are like. Sorry for people online if you don't see, but they are like one router with many outgoing edges, and then one other router with many incoming edges, right? And this makes this kind of structure like this with a lot of routers in the middle. And the way the layout algorithm works, it makes this kind of nice to see, but not very easy to interpret stars. And so when you see this, you don't really know where the traffic is coming and where it's going.
So if I get correctly, it means that these very long edges have no real meaning, right? No short, it's just
yes.
virtual here, right?
Yes.
So you could display differently what is long could become short. And
depending on how I choose the route node, for example, it could change. Now it's possible, and it's a future work that I don't do yet, but to weight the edges by the delay we measure, for example, from the source, to kind of try to have shorter edges for lower delay, higher edges. We can also change the coloring, so I could color by delay from the source. And for what we will see is that, for example, things in China will be kind of red, like with a high delay, but things in Europe will be more blue, like with a lower delay from the source. We could do this kind of coloring. Something that I don't show here. Yes, sorry.
But so you had at one stage this sort of huge flow of parallel lines, which are very long,
yes.
which are going east from east to west.
Yes.
They have no physical meaning, right? Just
so
long length. Right?
For instance,
long length.
So the fact that they are long, there's no physical meaning to this, but the fact that there's this bundle of line is that it's two networks which are highly interconnected. So this map is not it's more recent data than the one I've shown to you before, but in the presentation, these two big yellow blobs connected, it's probably like China Mobile and China Net connected together. Some two networks which are very strongly interconnected, but it's kind of an artifact of the layout algorithm that they are spread out. They could be as well very close. But obviously that's something that I would like to improve. So maybe I can tell you about the future works here, because don't need to show the slide. So one thing I would like to do is to make animation on this map. For example, we've performed 6 measurements a day from Ukraine to the rest of the internet, and we know that networks have been done in Ukraine during the war, and it will be very interesting to be able to have this map change over time and see things change and zoom and see where things change and so on. So I would like to animate this. Obviously, use delay information to make use of this information, so that we have a geographically based layout. Here I have a single vantage point, so it's measurement made from the ellipsis in Paris. But it's a partial view of the internet, right? Because if I were to, for example, we don't see the network of Orange or service provider, because typically they block measurements from the outside. But if we were to perform measurements from Orange, we will see part of the network of Orange, right? So one thing will be to combine multiple vantage points. But to do this, to combine multiple measurements, you need to be able to do alias resolution. You need to do to be able to say if two IP addresses belong to the same router. And I think alias resolution is even worse than geolocation, like it doesn't work. So because it's full of heuristics, so it's another problem. But also to include other data sources. So here it's measurements from the lab, but there's already a lot of publicly available traceroute data, like from CAIDA, ARC, Google MLab, not Google MLab, but just measurement labs, so RIPE Atlas, and so on. And also to highlight path, because here I know the path that we've measured from the source to handle this network, so it would be nice to say from here to here, this is the path that we see. And that's all. Thanks. And just to conclude, so feel free if you have any question. Also want to say that, well, basically everything I did was easy. I took things from other people and I put them together. But I really want people input, like how we can make this better, because I really think that this can be a useful tool for for people, to play with it and see what's the internet and so on. But maybe the layout algorithm can be improved. I don't know, lots of it. So it's very early work, also because I was working on this part-time. So yes. Il y avait Sébastien qui a.
One big question. So it seems that it's very easy to extend this to include the posts.
Yes, it's I could. It's just that in our database we basically drop this measurement data because it's a lot of data, and but I could keep it next time and add it here.
Because when I think it would be very interesting to see. So let's say I'm a victim of DDoS attack. I log the addresses of the hacked webcam, etc. I'd like to know from which network they are coming.
Yeah, and you can see it visually, right?
Yes. So maybe if I have yes, because here, if I don't know what you put, but if you search for an IP address, well, most likely the IP address I'm going to get is the one that is connected to me. So it's a host.
Yeah.
It's not just a router.
Yeah, you're right. And I would like to be able to show the position of the user, like when on the map you show where you are on the map, right?
Yes.
But yeah, I was thinking of taking the closest network to the user or something like this.
A question on that. Can you legally do that?
So sorry, do what?
Can you legally show IP addresses of people?
So
When you get the IP address when you connect to it. Yeah.
yes, so actually, I think I don't know if Timur is here. I think Timur is Timur here. Timur is not here, but actually, the GDPR user IP addresses, they are considered personally identifiable. So there's a debate in whether when you perform a traceroute measurement. So I don't know. So here I have no problem because we don't show them, but in fact, yeah, there's a debate in the community. Other platforms like RipeAtlas, which perform millions and millions of traceroutes every day, they show you the end IP address.
Yes, they are in the US.
No, they're in Amsterdam, in Europe. So the RipeNCC, but and they have lawyers. So I think it's, but in a sense, it's not in this way. It's not personally identified. In a website, it's because you know that this IP connected, and then you can check that it's connected to another website. But here we just know this IP is connected to this, but it doesn't depend on the user, right? If someone else, if you move away and someone else, no, but you're right. But that's a good question. And yeah, maybe if we do this, we should think about it before. Yes.
So it would be interesting since you have the RTP to have another representation, because I mean, which would look at the RTP distance between points. So and so
that would be physical meaning to
be more physical. Because I remember there was a very early paper by people in Israel where I think using this type of information.
Okay.
To claim that the graph structure was like the geometry of the internet was like hyperbolic geometry. They were looking at triangles and completing angles. So, but I think for that you can't just do, because what you have is just graph distance.
Yes, exactly. Yeah.
Nothing linked to geometry.
Yeah, so it links in the sense that the graph distance is the number of hops between the source, but that's nothing about the physical, the delay. Yeah, I agree.
Yeah, and so are people interested in geometric questions about this graphs currently, like what this is? It was 20 years ago.
Okay.
Like, this hyperbolic plane. Right?
So I think what at least I know of that people are interested is in the terms of maybe more structure of the graph. It's whether you have this core, then a layer around the core, and so on. In the way that things, how to say, like, is it a full mesh? I mean, more the kind of type of graph that internet is, right? Then about the structure implied, for example, by the delay, I'm not aware of this works, but I don't know. I don't know, but that's in fact a good question, and maybe this kind of questions are published in maybe a bit more mathematical publications. which well, I don't read so often, so maybe I'm not aware of this.
So in this order, proximity relates to IP address likelihood.
Sorry, IP address likelihood?
Like how many bits of difference in the IP address?
This that was the yes, the Hilbert curve drawing. This one, like it's based on the distance, but here it's based on the number of hops basically. So yeah, 2 IP addresses that are.
There is one thing for that, which is so because I mean a router has a certain there is a limit on the number of input
outgoing, yeah, incoming and outgoing edge.
Degree, right?
Yeah.
And so, how could it be that you have like these stars with a huge out degree?
But actually, so maybe Kevin, you can tell the exact number, but we've seen things like as many as 128 outgoing edges, interfaces. And so if you have 128 outgoing to, well, 128 routers and so on, it can make these very large stars.
Okay.
So actually, we do have very large, it's usually in networks like Amazon and so on.
Indicates the public interface with
data centers and so on.
Okay, that is very well connected to the. But for AX, I understand that it can be connected to a very large number of things, right? But for a router, which is a physical device.
Yeah, but yeah, they do in fact have yeah, tens of hundreds of like high speed interface outgoing to other routers to spread the load and also increase availability, right, in case of link failure.
Yeah, just in these graphs, the layout of the graph itself, does it follow the algorithm that you mentioned earlier about proteins and stuff like that, or it's similar?
Yeah, it's exactly. I mean, it's more subtle than that, but it's exactly this algorithm where you take the minimum spanning tree.
Yeah.
Take a root node, you lay out everything at distance 1 in the spanning tree, distance 2.
Okay.
And yes, the question of whether it makes sense to maybe I could lay out also only the minimum spanning tree, right? And not all the nodes which are around. But I wanted to see what we have if we have the most complete, excepted endost, but if we have the most complete graph. Yeah, and also I feel like so there's the delay information, but I feel like there's also maybe other information or the fact about the shape of the internet that we could use to make a better layout. Because, for example, when we have only a single trace route, so when we have only this, right? If I have this succession of links, then making the layout is very easy, right? I draw everything which has a distance 1, then 1 like 100 pixels later, I draw everything here, and the layout algorithm is straightforward. But when you start to add these thousands of trace routes which are all interconnected, I don't know. I'm not strong enough with graph to know the better layout. So this is why I use what other people have done. Yes.
So since you are interested in dynamical aspects, so people also try to look at traffic. Because I mean, so RTP is interesting, but I mean, there was a very interesting picture where you had the light, the sun coming, and you would see this IP addresses awakening.
Yeah.
But so this indication, but so traffic on the things can be measured by increase of RTP.
Yes. So I agree. It would be very interesting. There's 2 issues. So and Kevin, which is here, has written a paper very recently on this with other people on the need for maybe operators to communicate, or at least for the community to have access to traffic data, because you can measure it, as you say, by measuring, for example, the increase in the delay, which is like increase in the size of the queue of the router and so on. But it's a very noisy measurement, and it's a very noisy measurement because when you meet for for example, when I do this kind of measurement, here I can measure the delay between the time I send this message and I get the reply, and the same here. But the fact is, the messages generated by router, they are very low priority message, because the routers, they are more interested in forwarding the traffic than to say there's a problem. So basically, they do that with their CPU when they have time, and so it's to measurement. Even if there's no traffic, you can get very different. I mean, you can get like 3 milliseconds and then 5 milliseconds, and so it means that because, for example, here I can see 5 milliseconds from here to here, and from here to here I can see 3 milliseconds. So it will mean a negative delay on the. So it's unfortunately it's too noisy. So yes, there's kind of a call in the community to try to get traffic data because it's interesting, and also it's we can rank autonomous systems by their size, but we can also rank them by the amount of traffic they carry and so on. But we don't know this, so right now we can't. Yes.
That's a question for me at least. Do you plan to publish this tool on the website?
Yeah, I would like so. Well,
because I think it is for people interested in this topic, having this visualization, it would be nice to publish it.
Yeah, I would like so.
And then you would have feedback.
Yes, obviously. I don't think I can do it with this data because unfortunately it's a bit hard to share this data publicly. But if I do it with using other data source, I think there will be no problem. And yeah, and I really dream of something where you can choose whatever data source, whatever vantage point, whatever date, and you can compare graph also between maybe choose under layout and so on. Yeah.
Question on the bridge? Zero. So thanks again, Maxime.
Thank you.